All right, we're going to look at lesson 16. For this lesson, you will want to open the slides here in Google Classroom. And then you're also, pretty much for the rest of the year, we're going to be looking at the periodic table. So have this open as well. So let's go through the slides to begin with. So first, we're going to go through a couple of famous figures that helped develop the periodic table, kind of know the history of it, and then you're going to use it in a simple, kind of look at the basics on it, and that'll be the lesson. So first off, the periodic table, it really is like an amazing thing that nature is organized, that every little, it really is mind-blowing that every particle or every object you see is made up of tiny particles. And then those tiny particles can be organized by their behavior in this extremely predictable way. That's what the periodic table is. So it began with a French chemist, Antoine Lavoisier, Lavoisier, I don't know, it's French, I don't know, Lavoisier. I'm not sure to pronounce that, but Antoine L. started with a list of 30 substances, and he said, these things cannot be broken down any further. And he called them elements. Now, the thing is, he was actually wrong about a lot of this because a lot of them were combinations of oxygen and other elements that he couldn't break down. But he started with that. So 30 things you can't break down, he called them elements. And then we had John Dalton, who makes his own list of elements. Dalton eventually got to 60 elements. And same kind of thing, Dalton had certain things could be broken down, but he's kind of refining it, getting better. And then what happened is we started noticing trends and patterns. And so if you group them in certain ways, you could get it so that, elements in a certain row would behave a certain way, or elements in a certain column would behave a certain way. There started being patterns. And so what Dobereiner did is he grouped the elements by mass rather than just randomly grouping them in alphabetical order or something. He grouped them from lightest to heaviest. And you notice when you group them by mass, you start finding groups that have similar properties. So what Dobereiner did is he noticed that groups of 3 would have similar properties, and he called them triads. Now it ends up that Dobereiner, he was wrong and he was right. He was wrong about the triads. When you look at this thing, this is not groups of 3 that have something in common. It's much more complex. So, and notice it is, look, hydrogen has a mass of 1.008 grams. Number 2, helium, 4.003. Element number 3, lithium, 6.941, 9.012, 10.811. You see how that works? See how they're still grouped by mass? So Dobereiner was right to organize these things by mass. So grouping them by mass and finding similar qualities, that actually is how this thing is going to work. But he was wrong about triads. He was wrong about every 3 elements having something in common. He just found that at the time because we didn't know very much. So there were a lot of gaps. So it kind of worked out that way at the time. But as we discovered more elements, started organizing them by mass, his whole idea of triads totally got thrown off. So he was wrong about triads, wrong about groups of 3. But he was totally right about expecting certain qualities. They're expecting to find patterns when you group them in order of mass. All right, moving along. Then we have a guy named Newlands. He grouped them by mass again, but because he had a musical background, he expected to find patterns if you make them into 7 columns so that every 8th element is in the same column. He found some patterns. And so he called this the law of octaves, actually. And a lot of chemists of his day mocked him for it. They're like, you're trying to be a musician here in chemistry. He was wrong. Also, like Dobereiner, he was wrong. This is not grouped by every 8. There's a lot more to it. But he was on to something because there is something about having 8 valence electrons. That's why these are 8A. All these elements with 8 valence electrons, they all act very predictable. They have a lot of similarities. So he was getting somewhere, but he wasn't quite there. Here is the thing that really broke this open and basically paved the path for the periodic table we have today. We have a Russian chemist, Dmitry Mendeleev, and what Mendeleev did is he organized the elements by mass. He put similar chemical properties in rows. But what Mendeleev did, so say if we're back hundreds of years ago and we haven't discovered the element right here that behaves like the rest of these, behaves like group 4, and let's say we haven't discovered this yet though. So we have this boron thing with a mass of 10.81, and it behaves like everything in this column. And we have nitrogen with a mass of 14.07, and it behaves like everything right here. And it doesn't behave like anything in group 4. What Mendeleev did, instead of forcing nitrogen right here, where carbon currently is, and remember, I'm pretending we haven't discovered carbon yet, he would move it to right here so it behaves like all of these, and he would leave a blank space. That's what he would do. So anytime his pattern was messed up, he would leave a blank space, and he would just say, you know what we're going to do? We're going to discover an element that's going to have a mass of in between these, and it's going to act like everything in this column. So he made blank spaces to allow his patterns to work, because that is how it works, guys. The columns they all act similar. You can predict how and what an element's going to do based on the column it's in. And so he left blanks so that way his pattern of behavior wouldn't be messed up. So what he did is he left room for undiscovered elements, and he followed the trends and noticed gaps. And at first he was dismissed by other chemists, but they started discovering exactly what he was predicting. So for example, right here, what Mendeleev would have been able to do, if we hadn't discovered carbon yet, he would leave an empty space right here, and he'd say, listen, guys, we're going to discover something that's going to have a mass of in between 10.811 and 14.007 grams. It's going to have a mass somewhere in between there, and it's going to act like everything in group 4. And he would predict that, and boom, we would discover exactly what he would predict. So we ended up taking him very seriously because of that. And then also something he did that helped fix his periodic table is there's this large group that act different than everything else, and it's these guys right here where the drop down is. So starting right here from group 12 over to group 3. And so what he did, instead of forcing them in there and letting them mess up his table, he dropped it down a bit and just basically made the structure the way it is, because there's this big group, since they're filling up the D sublevel, they act very different. So he made them in their own little area in the middle. And once he did that, there's a lot of trends and predictable patterns in there. So he also made those transition metals. And so then Mendeleev formulated what we call the periodic law, which says that the elements vary with their atomic mass in a periodic way. Periodic means regular intervals. So basically what he's saying is if we group these by mass, there are going to be regular intervals to how they act, to what their properties will be. So if you group them by mass, there's going to be like columns and rows and pockets of behavior that's going to be similar. However, here's a problem. Remember what we did in the last lesson, calculating average atomic mass. Yeah, sure, the average weight of boron is 10.811. But what about if I have an isotope with a few extra neutrons? I could find a particular isotope of boron that's heavier than that. And maybe if I end up having an isotope of carbon that's lighter than that, these weights could get very similar if we have a heavy isotope of boron and a light isotope of carbon. And so grouping them by mass isn't consistent because their masses aren't always the same. But what is the same with every single boron in the world? They don't all weigh 10.811 grams, but every boron has 5 protons. Remember, we covered that the other day. The number of protons determines the identity of the element, and it does not change. So we have Moseley, who ended up discovering the way of, he developed the technology to count protons. And so what he did is he took the periodic law, and instead of grouping them based on mass, he says let's follow them based on protons. Now granted, the average masses still work. It still goes in increasing order, but because the masses can fluctuate, we organize the periodic table now not by mass, but by protons. So 3 protons, 4 protons, go over here, 5, 6, 7. You'll notice it's a very consistent number. So that's what Dobereiner did. That's what Moseley did. What we did by World War II, everything up to atomic number 92 had a place in the table. And then what we did during World War II, while researching for the atomic bomb, we produced a bunch of elements in labs. And there are 2 of them you can find small amounts in nature, but most of them are just developed in labs. And so what we call them transuranium elements. So I'm talking about these. Oh, you know what? This table doesn't even have the transuranium elements. No, I'm sorry. It does. It does. Look right here. Go to 92. Right down here, uranium. Everything with a number higher than uranium, we call it transuranium or after uranium. So look at the names of these: neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium. Who do you think that's named after? Nobelium, lawrencium. You can kind of see how all of these, you can kind of tell by their name. Look at Copernicum, Nicholas Copernicus. So all these elements after 92, Rutherfordium, we learned about Ernst Rutherford. All the borium, we learned about Bohr's models. So all of these past 92 are, for the most part, discovered and created in labs. So they're the transuranium elements. All right, let's get back to where we were. So then, so the periodic table is organized in this way. First off, we have the atomic number, which is the number of protons, and we find that on top of the cell right over here. We have the name, which is below the symbol. So let me change this. This slide was prepped for a different periodic table, so I'm going to edit this. The name is below the symbol. The symbol is the 1, 2, or 3 letter symbol, and it's the biggest item on the cell, the big old PD, big Ni. The atomic mass is under the symbol. The atomic mass is down here, and this is going to be the weighted average. This is not what every single one of these elements will weigh. It's what their averages are. And then sometimes you'll have the electron configuration and the physical properties are sometimes on periodic tables. I've given you a very bare bones one that doesn't have much of that, but sometimes you'll see those on there. So there are 2 different ways of naming the vertical columns. First off, we call them either a group or a family. So like you'd say this right here is group 8 is what you'd call this right here, or group 11. Or, so there are 2 different naming systems. The IUPAC system, we number them 1 through 18. So see right here up on top, number 11 right here, number 12, 13, 14, 15. That's the IUPAC system of naming these columns or groups or families. So family 4 would be right here, and it includes all of these. So there's the IUPAC system 1 through 18, and then there's the NACPT system, which is based on valence electrons, and it has an A or a B, and it numbers differently. So you have 1A, 2A, 3A, 4A over here, 3B, 4B, 5B. So you have B's over here, and you have A's over here. So B's and A's are what it uses in the NACPT system. So vertical column is called a group or a family, and then the horizontal row is called a period or a series. It's not labeled right here, but period or series 1 just has hydrogen and helium. Period or series 2 has lithium, beryllium, jumps over boron. This right here, starting at sodium, is series 3. Right here we have series 4, 5, 6, and 7. So we can number the period of series 1 through 7 down here. And then we have the groups or families. For now, we'll use the IUPAC system of numbering 1 through 18. So like if I said, tell me what carbon, what family and what series is carbon in. So what you do is you say, where's carbon? Okay, it's in group or family 14. And then what period or series is it in? It's the second row down. So carbon is in group 14, period 2, or series 2. Okay, so you just say the column and the row. So, and then this is actually something that, I'm going to pull up a different periodic table to show you this real quick. Let me show you this. When we group them, there are 3 different broad types of elements, and you have metals, which is group 1 through 18, and the bottom of group 1 through 12, and the bottom on 13 through 18. So 1 all the way to 12, all of these things are metals, and then these shaded things right here, below them we still have metals, okay? So metals are a huge portion of the periodic table. All the way up to these shaded ones right here are metals. And then above the shaded area are the nonmetals. So all this yellow and light blue are nonmetals, and then the metalloids are these right here. So you have the metalloids right in between the metals and nonmetals. Yeah, if we were in class, I would give you your own copy of the periodic table, and you would be labeling and shading in and coloring this stuff. So I would say if you want to print off your own periodic table, you could do that, and you could shade in these metalloids, or just write this down somewhere. And remember, the metalloids are BSIGEASSBTE, and then all the metals are to the left of those, and the nonmetals are to the right of those. So I'll be reminding you guys of this later on when we start using it. That's something else you'll need to know. So using this, you're just going to answer these questions based on what I went through earlier. And then I'm not going to do all these because I want you to try them, but I'll go through a couple with you. Let's go ahead and do one right in the middle. Period 15, family 3. So all you're going to do for this is you're going to go to the periodic table. Period. Oh, you know what? These are backwards. Oh, okay. Yeah, so I'm going backwards. I'm messing this up. What period in family do you find helium? So right now these are backwards. This needs to be saying family 9, period 4, family 11, period 6. By the time you get this, I will change this. I will fix that, okay? So I'm going to fix that typo. So imagine right here it says family, and right here it says period. Helium is all the way over here in family 18, period 1. So that's why it's a typo. So you should pick this one right here. It's going to say family 18, period 1 by the time you get it. So I'm going to fix all of those. So really for these, you're just going to find them and say what family and period they're in. Right here, atomic mass of 121.6. So for that, it means you're going to look at the masses down on the bottom, and we'll go here, 121.6, right here, tellurium. Okay, and then so you'll say it's in family 16, period 1, 2, 3, 4, 5. Family 16, period 5. So right here. Yeah, so I got some typos on these answers. I'm going to fix these answers by the time you're taking this. But yeah, this one is in 16 and 5. So, which isn't even listed here. So I got some typos. By the time you take this, I'll fix these typos. But that's how you look up the atomic mass. And then where do you find Na? So just look for the symbol Na, and you'll have your answers here. And then lastly, you're going to go to group 8, period 6, or group 16, period 2. And once you're there, you tell me which element is there. That's all you need to do for this. You'll just get used to looking around the periodic table. I want you to get more and more time doing this so you start finding stuff quicker in the table. You'll start knowing where things are and not having such a hard time with it. So as always, email me if you have any issues or questions. And like I said, your current view of this, these answers are all backwards, but they will be fixed by the time you take this. All right, have a good day.